Hello.
Hey, McKinley, what's up?
Nothing. Just taking my driver's test after this.
No way.
Yeah.
You ready for it?
Mostly
What do you do at a railroad crossing?
you stop and look and make sure.
Always?
What?
Always?
Yes, always.
Do you know the difference between a guarded and an unguarded crossing?
Yes, I know the difference.
Who has the right of way if it's a four-way and you come at exactly the same time?
The right guy.
Whoever's on the right. I think you're going to do fine then.
I'm gonna zoom.
How much snow did you guys get?
A lot. Like too much.
It's supposed to snow again tonight.
I know. Like we got like they made it like we had like a bunch of snow drifts in front of our house, so we like
Jumped off your roof into it.
no, we didn't do that. Ella and Gavin, my younger brother and sister, they made a
Snow cave?
like a snow cave in one of the
Nice.
massive drifts.
Yeah, this is a good time to do it because it's all wind packed, so it's nice and solid.
Yeah.
My brother tried making a snow fort, but then it kind of got collapsed under my crushing body weight.
We used to do that in the Army all the time, and then we would have to sleep in them overnight. All right, well, it looks like you two are the only two showing up, so we'll get going here. Any questions on the algebra review stuff?
I have none.
All right. Moving on. So we're going to start chapter 11. Chapter 11 is area. Chapter 12 is volume. So these are the two chapters that, kind of probably what you thought geometry was going to be like, shapes and formulas for area. So these are those two chapters. Now, last chapter was the easiest one in terms of test. This would be the next two chapter would be the next two easiest ones. Some of the formulas you're already familiar with, other ones you won't be familiar with, but they're basically just formulas. It can all go in your book of truth, so this one isn't too challenging of a chapter. Here's your homework.
Why they're
Speaking.
why?
Why what?
Why do you have like I don't know.
I wanted to pick some interesting problems here. All right, here we go. So yeah, technically this section is on area of rectangles, and probably both of you already remember the formula for area of a rectangle. But I will say this, since I was your algebra and your pre-algebra teacher, I mean, I never proved to you that the formula was length times width or base times height. I mean, I just said it. You guys all accepted that I wasn't lying to you, and I wasn't, but I never really proved it to you. You're going to see today the reason why no one ever proves it to you until you get to high school, because it's a complicated proof. So here we go. There's a bunch of postulates and theorems today. Just one theorem, but three postulates. We'll start off with some definitions that you should be familiar with. Now, this is a new definition. It's one that we've already seen before. Quadrilateral, quad meaning four, lateral means sides. It is a polygon, so many angles. So it's a polygon. Remember, polygon is also a closed plane figure made up of segments joined at their end point. So this is a polygon with four sides, all right? One specific type of quadrilateral, remember we had four of them, I believe. let's see, rectangles, squares, trapezoids, parallelograms, and 5 of them. The one that we'll be talking about today, or one of the ones, will be a square. So that's just a quadrilateral with 4 right angles and 4 congruent sides. And then lastly, and this is for the entire chapter, what we're doing today is we're calculating the area of the space enclosed in the shape that we're dealing with. Today it's going to be rectangles. Okay, so those are some basic definitions there. We've seen them all before, with the exception of area. We haven't seen area this year, but we've seen it in the past. So we'll start off with squares. Squares are a quadrilateral where all the sides are the same. So 4 congruent sides. Just so you understand closed, I know I've said this before, there are 4 sides right there. Closed means that you can't get to the inside. Now I can get to the inside of this, I don't know, question mark looking thing. It's got 4 sides, so it is technically a quadrilateral. It's got 4 sides, but I can't get to the inside, or I can get to the inside if it is closed. In other words, like the square to your left, if it's closed, I mean, I can't get to the inside. If I try to get to the inside, I have to cross over one of the sides. So that's
Well, then you just erase one of the sides. There.
Well, agreed. Then it's a triangle because it's got 3 sides. All right. So that's this basic idea of closed. Plane, just remember we're talking about things that are on a flat surface, and it does have 4 right angles. All right. So that's our basic definition of square. Here comes your first postulate. Remember, postulates we accept to be true. And this one says, well, it claims that the area of a square is the square of one of the sides. Now, I'm not going to prove it to you because it is a postulate, but it should be self-obvious to you. Well, if this is, I'm going to claim that this is a square, and that square has a side length of 1 unit. So if I make a larger square, say out of another square, so if I just duplicate that square, I've made a rectangle now. To make a square, I would have to add 2 more squares. And therefore, the area of that would be 4 of those tiny squares. So the area is 4 square units. And I can continue that onward, make larger squares. So it's kind of like, I don't know, your Lego model of making things. I just add more squares, I make larger squares. But once you've established that it is a square, you can take any one of the sides. In this case, there's 4 of them, so 4 units long, and then square that number, and you get the total number of squares made to make that square. Now, I've said square like too many times there, but I think you get the picture there. So you take one side, you square it, you get the area. All right, and that is a postulate. We're not going to prove that one, but I basically showed you the basic construction. Now, notice we make a rectangle. I didn't make a rectangle, but if we make a rectangle, I'll make a crummy one right here in a second. If we make a rectangle right here, we don't have a formula yet for that rectangle. So here's a rectangle made out of squares. It appears that there might be a formula, but it's a pretty broad claim. So I'm going to have to prove that one to you for rectangles. All right, these are going to come at you pretty fast and furious now. This is postulate 18. Here's what it basically says, that if you have 2 shapes that are congruent, remember congruency means same shape, same size. So if I have 2 triangles that are congruent, then by that idea that they are the same shape and the same size, therefore their areas must be equal as well too. So postulate 18, it doesn't say much, but it does say that if you have 2 shapes that are congruent, well, then their areas must be equal. So that one's, once again, a postulate because that would make sense. So postulate 17 gives you area of a square. Postulate 18 gives you area of congruent shapes. Tell me if I'm going too fast. And then the last postulate of the day, we okay to move on?
For me, yes.
Okay. So the last postulate says this. Don't write this down, just look at this. If I have a shape, it's a pentagon here, and I break my pentagon up into a certain number of non-overlapping shapes. In other words, I went from D and just made some diagonals here. So I broke it up into 3 smaller triangles. And I add up all 3 of those triangles, the area of each one, well, then it must be equal to the area of the larger shape. And that's what Postulate 19 says. Take any large shape, break it up into a series of pieces parts, and then add up the areas of those pieces parts, and you get the whole darn thing. So it says the area of a region is the sum of the areas of the non-overlapping parts. And then I put in there, you know, remember we had the segment addition postulate. The larger segment is made up of two of the smaller ones. We had the angle addition postulate. It's made up of the sum of the two smaller angles. Well, this is like the same thing, but for area. So the area of the large is equal to the area of the parts. And that's postulate 19. So 17 was square area. 18 was congruent. Shapes have equal areas. And postulate 19 says you can take a larger shape and break it up into a bunch of little smaller shapes, calculate the area of the smaller shapes, and that'll give you the area of the larger shape. Nothing earth-shattering there. 3 easy postulates. There's nothing unique about how I named them. We could have named anything. And I think I've showed you this before. You can take any polygon. Here's a hexagon, right? You can take a hexagon. And if I take that hexagon, put a dot in the middle and connect the dot, I break it up into a series of triangles. And it would be the same idea that if the area of triangle 1 plus the area of angle triangle 2 plus the area of angle 3 plus the area of angle 4, triangle 4 plus the area of triangle 5 plus the area of triangle 6, add up all those areas and you get the whole darn hexagon. Okay, we ready to move on?
I am.
Okay. One more definition. So rectangle, and that is what this entire section is about. It's about rectangles. So rectangle is a quadrilateral, 4 sides, and it has 4 right angles, and that's where it ends, right there. 4 sides, 4 right angles. That's the definition of a rectangle. 4 sides, 4 right angles. So
That's underwhelming.
4 sides. It's got 4 right angles. Therefore, it is a rectangle. Okay.
Yes.
Okay. So also write this down. We are going to define the base of a rectangle as any one of the 4 sides. So it's not that the bottom is always the base. It could be the top. It could be the right side. It could be the left side. Any side of a rectangle could be the base. Yeah, generally we're lazy. We always make the bottom the base. Now, we use lowercase d italicized for base. The height of a rectangle is the perpendicular distance between the base and the opposite side. Now, since it is a rectangle, if we slide this red height over to the right or left, we wind up it being one of the sides. So more likely we call the height one of the sides. Okay. And I guess what I'm saying here is that our traditional dimensions of length and width, somewhere between pre-algebra, algebra 1, you guys probably started saying base and height, and we will do that in this book as well too. So yes, there is a length, there is a width, but we generally just say base and height for rectangles. Just remember, height has to be a perpendicular distance. Okay?
Yes.
All right. So we're only going to do one proof today, and boy, is it a challenging proof. And it is literally the proof of y is area of a rectangle equal to length times width or base times height. So you probably encountered this sometime in 4th grade, and they gave you the formula, and they said, hey, area of a rectangle is length times width. None of you probably asked why, although maybe, but if you asked why, the teacher probably said something like, well, because I said so, or it's really hard to give a solid proof to why the formula is length times width. And you're going to see, I'm going to give you a proof, and you're going to see that you actually needed some high school math in order to make this true. And then the reason is I mean, you can get a kid to, and when I did it in pre-algebra, I basically showed you a bunch of squares just all stacked on each other. But my claim was that those squares will fill up the rectangle. And that's a pretty broad claim. So we're going to do a rigorous proof, and this will absolutely, no doubt, prove it to you. But this is also why it can't be done in 4th or even up through 7th grade. All right, so here's my proof. So my proof is going to start out, well, with a rectangle. And I have a base of B and a height of H. And we just said from the previous slide that the H is one side and the B is another side. So I need to just take that basic given, which is it's a rectangle with base B and height H, and I need to somehow get all the way down there to area is equal to base times height. And you're going to see how complicated this is. All right, so here we go. So the first thing I'm going to do is I'm going to extend one of the sides of my rectangle. So I'm going to extend each side of H, right? So where H is, now it's a parallelogram, so H is on both sides. So I'm going to extend each H, like I'm extending these straight down. Now, one side of H is parallel to the other side. So as I extend them down, they remain parallel. And I'm going to extend them down for a length of B units. In other words, that red dotted line that I just made there, and the other one on the other side will be length of B. Okay? And I just do that through basic construction. Now, it will make sense that I should play connect the dots there, and let's see if we can tease out what's going on here. Well, let's see. If B is parallel to this side, which we'll also call B, and we extended these down for length of B, then if this is, and that would make this side parallel to this side, and if this was 90 degrees, then this would be 90 degrees. In other words, I just made a rectangle again. So I made another rectangle with that basic construction, okay? So that length must be B as well too. In fact, I just made a square. That red dotted line is a square, okay? We'll do the same thing with side length of B, except this time when I extend B, I'm not going to extend it B, I'm going to extend it H units long. And just like with the previous one with B, you wind up making a square, right? So that length right there would also be H. So I've got a square. And then if I continue down here, well, I don't have a square, but look, I've got another rectangle. Let me close it up. I got another rectangle with a length of B and a width of H. In other words, I now have two rectangles. This one right here, we'll call this one 1. And we'll call this one 2, and both of those rectangles are exactly the same. Why? Because they have length of H and a width of B, okay? The other two shapes right there, right? The other two shapes right there are squares. So I have, I'll do this one in green. So I have a square right here, and that's got side length of H, and I've got a square right here, and that's a side length of B. Up to this point right here, okay, I can see all that. Where am I going with that? All right, so here's where I'm going with that. What I'm going to go with that is that well, I'm going to go with what I first said, that these two rectangles right here have the same area. I'm going to claim that they have area equal to A. So I'm just throwing in a variable, capital letter A. So they both have an area of A. Why can I say that? Postulate 18 says if you have two congruent shapes, then their areas must be congruent. So they're congruent. Why? Because they're rectangles with side lengths B and H, so therefore they're the same size, and therefore their areas are congruent. Okay, I'm not claiming yet that I got that by multiplying B times H. That's where we're going. The second thing is that I can say something now about I need another color. We'll do pink here. I got to say something about this. Oops, sorry. I got to say something about the large shape right here. In pink, I have a large shape, And by the way, it is a rectangle. In fact, it's a square. Why is it a square? Because it has side lengths B and H on one side, B and H on the other side. I didn't label this. B and H on this side and B and H on this side. It's a square. All four sides are exactly the same. And all four corners are right angles. Therefore, it is a square. That's a lot of pink there. Let me erase that. Therefore, it is a square. So the area of the square, would be equal to one side length. That would be H plus B squared. Okay. Well, and that's postulate 17, that the area of the larger shape is made up of, 17 is that if a square, then it's one side squared. There's another way I can write that. So the area of the big one would be equal to, this is postulate 19, says that if we take up all the little pieces and add them up, we will also get the area of the big. So let's do that. So the area of the big, well, I've got two A's. A, remember, stood for area. I've got this square right here at the top. All right, the square at the top right here, that is H squared. It's not drawing for me. There's H squared, that's a square. And then I have this square right here, well, that's B squared. So that's two A's plus H squared plus B squared. All right, both of you tracking what I did so far?
Yes.
All right,
Yeah.
McKinley, you're up. I want you to take a look at, since we're already in our fourth quarter of algebra, I want you to take a look at these two statements right here and tell me what I'm going to do next.
Probably combine them together.
That's why you're in quarter 4 of geometry. Very good. So by the time you get to quarter 4, you've seen this trick done so many times. This is just a substitution. All I'm going to do is set those two equal to each other. Very good. All right, Ben, do you remember how to square a binomial?
I'm pretty sure.
Tell me what to do.
Maybe. So when squaring a binomial, you
Silence.
yeah, that's how.
All right, I'll give you a hint. Remember stacking them? So I've got H plus B times H plus B.
Yeah.
Now what?
Well, then you would just dip.
Second hint.
You would add them together.
Oh no, we're squaring.
Oh, squaring.
We're
You
multiplying.
multiply them.
Well, let's multiply them together. Tell me what to do first.
And first you so you multiply. Oh, wait a minute, I remember this now.
Exactly.
So first off, you have to figure out whether you're going to, since you're multiplying, you have to figure out whether they're going to be positive or negative.
Well, positive times a positive is positive.
So it's a positive, so that's quite easy. So then you just take the H, and then you take the other H.
If I ask you to multiply 42 times 13, what would you do?
I take, oh, fine. We multiply the B, and we get do the B's.
And that would give you?
2B.
No, it wouldn't.
B squared, whatever.
Well, it's a big difference between 2B and B squared.
Yes, I understand that. And then we have, plus, and then we have H squared, and then boom.
Whoa.
Oh, wait, no. Then we have HB.
I'm going to choose to write that as BH, but you were right. Okay. Now
And then we have BH squared because there's two BHs.
No. Okay, so you did 3 times 2 is 6, 3 times 4 is 12. Then what did you do?
Then I took.
Well, you can say you drop down, add a 0.
Yeah. Then you have BH.
Agreed.
And then you have H squared. So then the final result is H squared plus BH equals B squared. H squared plus BH squared 2BH.
There you go.
Equals B squared.
Plus B squared. All right. McKinley, did you follow all that?
Yeah, but I thought you were gonna do the method of h plus b minus h plus b, and then just kind of cancel it out.
Well, it is one of those special case ones, but you know, how many people remember the special case? I mean, you guys have already forgotten. That's why way back when in Algebra 1, and I was teaching you, hey, the stacking method, I said that if you learn the stacking method, you won't forget the stacking method, but you were absolutely 100% forget that this is one of those special squares of binomials. And if you remember the rule for special binomials, that's h plus b squared. It's the first thing squared and the second thing squared, and then it's double the first plus the second, and that's literally what we just got. It's the first thing squared plus the second thing squared plus double the first two added together. But nobody remembers that. All right, so we just did what Ben just said, and that was h squared plus 2bh plus b squared equals 2a plus h squared plus b squared. Now we're just simply going to do a little bit of algebra. I think, McKinley, you were saying to do what now?
No, I was saying just put them on top of each other and make one negative.
Well,
and then add them together.
How about we just do some algebra right here?
Oh.
Notice I got an h squared on this side. I got an h squared on this square.
Oh, you can cancel them out.
You can. Well, subtract, right? I got a b
subtract,
squared.
Yeah, can.
So if we subtract those, what will be left with?
2bh equals 2a.
Okay. And guess what happens if you divided both sides by 2?
They would, the 2's would disappear.
And you would be left with that, QED. There you go. Area is equal to base times height, or length times width. Now just think about what we just did. We did all of that just to prove something that we knew from 4th grade, that the area of a rectangle is length times width. But look at what we had to do to prove it. We had to use quadratics, right? We had to square a binomial. No 4th grader knows how to do that. And that's also why no teacher ever proves this to a 4th grader, because, well, they can't do this sort of math. But you just can. You just did. And by the way, we just proved the fact that the formula is in fact true. So we can now enter this into our book of truth. There it is. If you have a rectangle, it's equal to length times width or base times height. Now the book is going to use base times height. It's just easier. And that's the only theorem today. So we did 3 postulates and 1 theorem.
So we're only doing rectangles this chapter and then circles next chapter? Or
No, we're doing all polygons this, I mean, literally all of them. Literally all of them. That sounds like a pretty bold claim, but we are going to do all polygons this chapter.
Okay.
Notice in 8th grade, we only went up to trapezoid and we stopped. We talked about hexagons. We never calculated area of a hexagon. We talked about octagons. We never did area of an octagon. We talked about dodecagons, and we talked about, what was the largest one we talked about? I think dodecagons were the largest one we talked about. But we will calculate the area of all of them. It turns out there's one formula, so it makes it pretty easy.
Okay.
Remember, we're calculating area, so all of our units will be in square units. So if you're doing in centimeters, centimeters squared, miles squared. If there are no units, you will put units squared. All right, if this was 8th grade, I would show you a nice friendly rectangle and say, what's the area? But this is high school geometry, so they will not give you a nice friendly rectangle. They will give you some ugly shape. Remember, this is called a compound shape. It's made up of more than one shapes. So McKinley, how many shapes do you see here?
I see a rectangle as well as a square.
Yeah, possibly a square. We don't know if it's a square, but we certainly see, what, 2 rectangles there?
Yeah.
Now I'm going to show you 3 different ways of doing this one problem. You don't have to do all three ways, obviously. You can pick whichever one you see. So actually, no, I'll let you do it, McKinley. Where do you want me to draw a line?
At the very corner where 2 is, draw a line all the way to the left side.
Oh, good. That's the one that I chose as well, too. Okay, so just like that. There we go. Okay.
So now it's just 5 times 8 and 6 times 2.
Yeah, but you got to be careful because that 5 goes from where to where?
Oh, it goes from both sides. So you would have to put it in half.
Well, I mean, let's just label. Like the 5 goes from here to here, right?
Uh-huh.
But in order for me to, for my rectangles, right, I just need this piece right here to stop right there. So how long is that piece?
About 3.
It is 3, right?
Yeah.
You got that from the fact that there was a 2 right there. Okay, so let's see. The area of, I'll call it the weird shape, right? An L or something like that is equal to, if we had to give names to it, we'll have region 1, right? And we'll have region 2. Now, region 1 and region 2 are both rectangles. One of them is big, one of them is small, so I'll call it the small rectangle plus the big rectangle. McKinley, you said that the big one was 8 and 3, and what's the small one?
6 and 2.
And that's what we'll throw in. And then from there, it's pretty easy to get to our answer. Remember, the units must be squared, unless it says it's centimeters or something like that. All right, very good. There's one way of doing it, Ben. You got to think of another unique way of doing this, not the way that McKinley just did it.
All right, well, so I have an idea.
All right.
So let's draw a line from the corner where, one sec. Actually, can I draw it on the board using
Sure.
the annotate method? All right,
Go for it.
perfect. All right, so well, I'm gonna draw a line from here. You guys can't see what I'm drawing until I let go. So I'm gonna draw that line. I'm gonna draw this line.
Ooh, interesting.
So what we do basically, we just pretend that these two lines don't exist. So we just got one big rectangle. We take
One big rectangle of dimensions what?
5 and 8.
Okay, well that would give me 40.
Yes, we got 40. But now we gotta take into account of the shape right here.
What do we want to do? Add to 40 with that?
Oh no, we're gonna subtract this from 40.
Correct.
So we're gonna take. So first we got to figure out the dimension of this side, which is fairly easy. We just take 8 minus 6, so we get 2 here.
Okay, and the other side is 2.
So now we just 2 times 2 is 4. So now we just. I cannot. One sec. All right, I had to. I had to. Yeah, and then boom, here we go. But that's the answer.
And notice we got exactly the same thing that we got on the previous one, and we better, right? Because it's the same shape. We didn't change anything. All right, very good. McKinley, can you think of a third way of doing this one?
Guessing.
Giving the answers away here.
Well.
I did it again.
I can't. From that line where 2's hanging out, just go straight up.
There you go. And I know as I saw that. Okay. So
Right.
we got, well, the big one, we got a 5 and a 6. How about this little one?
That would be a 2
and
a 3.
There you go.
Yeah, and
So
then
that would give us 40
plus
Well, that can't write because this side is not 8, it's actually 6. Okay. So 6 and 5 is not 40. 6 and 5 is
Math mistake.
Well,
yeah,
no,
that's 30
plus
6.
And there is another way of getting to 36. All right. We've beaten that dead horse. We don't need to do another one. I had another one ready, but we don't need to do that one. Okay. And that one was the one that Ben was saying with different numbers. Okay. I do want to show you because everyone always complains about the tables, and they'll say, hey, how do you do the tables? So this is classroom exercises. This isn't homework, but the homework will have you do a table as well too. So notice it says refer to rectangles. So all of these are rectangles. We got base, row, we got a height row, and we got an area row. So we start off with our basic area is equal to base times height. And then we just plug in what we know. McKinley, pick one. 6 through 13, pick one.
I feel like 13 today.
All right, so what does it tell me to do? It says,
You do area equals x plus 3.
why am I putting it in parentheses?
Because we're going to do outside multiplication.
You got it.
Or distribute there. All right, so you get x squared plus 3x.
All right, you got it. So area is equal to x squared plus 3x. And that's kind of weird, but that's not what we expect as an answer. And that's all in units squared. I don't have to put it in parentheses, but I did. Units squared. Otherwise, it looks like it's just the 3x that has the word units squared on it. Okay, very good. Ben, pick one.
Of the table?
Yeah.
Well, let's do number 6.
Number 6, really?
No, I'm just doing easy ones. I don't know. Let's do number 9 because it's the other one I went to.
And number 9 is a little bit different. All right, so area is equal to base times height. We plug in what we know. What are the two things we know on number 9?
We know that the area equals 55 and that the height is 5.
So we don't know B, but we do know 55.
Well, an easy way to solve this is basically divide each side by 5.
So therefore, B is equal to
11.
And the units would just be the word units, not squared because we're solving for base or height. All right, there we go. So that's how that table is done. Okay, don't panic when there's some square roots, right? You could multiply, McKinley, these two together. Multiply those two together.
It would just equal 10 root 3.
No, it would be 10 root
9.
9.
And the square root of 9 is
3.
So therefore, it's 10 times
root 3.
If
root 3.
Just regular 3.
Therefore, the answer is
30.
If you're multiplying two things that have the same root, instead of writing the 10 root 9, you should just say 10 times 3.
I'm with you, Ben.
Because no matter what, you're always going to get it.
Correct.
Root 4 times root 4, you get root 16.
The square root of 2, what Ben's saying is, don't write the square root of 4 and then take the square root. Well, when you square, what this is really saying to do is take the square root of 2 and multiply it by itself. In other words, square it. And the square and the square root would cancel each other out, and you're left with 2. And I agree. That's the smarter way of doing it. All right, that's all I had for you today. Where are we at? 40 minutes, so about 10 minutes left. Any questions on anything we did?
None for me.
No.
One last thing. We didn't talk about perimeter. The homework does talk about perimeter. We talked about it the other day in class. We were talking about formulas for a rectangle. What's the formula for perimeter of a rectangle if it has a B and an H? What's the formula?
B plus H plus H.
Or 2B plus 2H, either one. There you go. Easy enough. No other questions?
Nope.
I'm not sure. Oh, we had one other person join us. Who's here? Oh, no one. There's just
nobody's here.
Yeah. No idea why they blew us off today. They're usually everyone's already here. All right. Well, I got nothing for you. Good luck on your homework. I'll be online until about 8 tonight. So if you haven't run into any problems, just send me a quick chat.
All right. Have a nice day, Mr. C.
You as well. See you tomorrow. Hopefully you don't get too much snow today.
Yeah. Goodbye.
See ya.